Hi there, this is Math 6, Unit 5, Lesson 6, Methods for Multiplying Decimals. And today we're going to look at different ways we can represent multiplication of decimals. Okay, so here we go. First of all, we have activity 1, which says which one doesn't belong, talking about products here. So which expression doesn't belong? Explain your reasoning. So you have 4 different options here. I want you to take a look at them and decide which one do you think doesn't belong. And again, as always, there's not a perfect answer. It's more about you having a conversation with your classmates about what do you notice and which one do you think makes the most sense for not belonging, and give some rationale for that, for why you think that. So for example, you might look around and go, well, let's see, this one has a 2 in it right there, and this one has a 2. So you could say that this one doesn't belong because it's the only one that has a 2 times 3, has 2 whole numbers being multiplied together, whereas the rest all have a single digit being multiplied together. That could be there. You might notice that these all have a 0.1 or a 1/10 here, and this one has a 0.3 or 3/10, so maybe that one doesn't belong for that reason. Up to you, whatever you might say. You could look and see, typically it's a whole number times a decimal, whole decimal, except this one where it's switched around. So maybe you notice just the order things are written in. Again, no right or wrong, just something you have a conversation about with your classmates. So move on to activity number 2. Using properties of numbers to reason about multiplication. It says Elena and Noah used different methods to compute 23 hundredths times 1.5. Both computations were correct, so just keep this in mind. They're both right, okay? But here's Elena's method and here's Noah's method. Analyze the two methods, then discuss these questions with your partner. Which method makes more sense to you, and then why? And then what might Elena do to compute this product here, and what might Noah do to compute it there, and will they result in the same values if they do it their way? So when we take a look at Elena's here, first of all, we have the problem is 0.23 times 1.5. And we can see, first of all, Elena, she took the 0.23 and she multiplied it by 100. In doing that, what do you notice happening with the decimal? The decimal moves from being here as a 0.23 to, in our solution, it becomes simply 23. So the decimal is moving, because we're multiplying by 100, 2 places to the right to end up at 23 right there. Okay? You multiply by 100, which has 2 zeros, we move the decimal 2 places to the right. So she's converting the decimal into a whole number. She does it here as well by multiplying 1.5 by 10 to give us another whole number. Again, multiplying by 1 0 means moving it to the right 1 place, and so we end up with 15. Then we can see she takes the 2 whole numbers and then creates a new multiplication problem and multiplies them together to get 345. Okay, well that's good so far, but we can't stop there. We know she keeps going. She then decides to divide this answer, right, 345, by 1,000. Dividing by 1,000. So where does that come from? Well, we multiply by 100, right? We multiply by 100 here, and then we multiply by 10 there, which is a total of how many zeros? 1, 2, 3. It's multiplying by a total of 1,000 altogether when we change the decimals around. So it makes sense that to put it back in the proper form, she has to do the opposite, which is going to be dividing by 1,000. So she gets to 0.345, okay, or 345 thousandths, tenths, hundreds, thousandths is how you would say that. For Noah, he took the 0.23 and wrote it as a fraction, 23 hundredths. He had the 1.5 and wrote that also as a fraction for 15 tenths. And you might not normally do that. That may not be something you look at, but we know it ends in the tenths place, so we do the 15 and keep the place value there, tenths. And then did straight multiplication. 23 times 15 was 345, and 100 times 10 is 1,000, which is what we did right there. To end up with 345 over 1,000, or rewritten as a decimal, is just like that. Both methods work just fine. We can tell that Elena wanted to use what she knew about place value and multiplying by 10 and 100 to make whole numbers, and Noah wanted to keep everything in fraction form and then put it at decimals at the end. Either way, it works out the right way. So the question is, which one makes more sense to you, and why would you do that? And that's a conversation for you to have with your classmates right about now. Okay, and then we take a look at what they might do. Elena, what would she do to do this? Well, we would say she'd probably multiply 0.16 by 100 to move the decimal over 2 spots. She'd multiply 0.03 by 100 to move it over 2 spots. Then multiply those together, and then she'd have to divide by 1, and we have 1, 2, 3, 4, 1, 2, 3, 4, divide by 10,000 to put it back as a decimal. That's probably what she would do. Noah, what he would do is probably write this out as 16 hundredths times 3 hundredths, and then multiply that out to figure out what that's going to be. So it'd be some number over, again, 1, 2, 3, 4, 10,000 there. So both would work. You'd end up with the same value. You just have to decide if you want to keep it in a fraction form or decimal form, and it would work. So let's take a look here. Let's compute each product, number 2, using the equation 21 times 47 equals 987, and what you know about fractions, decimals, and place values. So we already know that 21 times 47 is 987. That's a given for us. We're going to see the same numbers here, but what do you notice? We notice that the decimal points are in different places there, which means we've changed something to our original over here. So for example, okay, this one has gone from 21 to 2.1, right? It's gotten smaller there from what it was before. We started with 21 times 47 equals 987. That was the idea. So with our numbers here, we could have the same numbers, or the same digits, so to speak, but the place value is changing. In this case here, we moved it 1 to the left there. We've also moved this 1 to the left there, which would be like dividing by 10, and this is dividing by 10. So in total, we divided by 100 from the original answer we had before, which means we need to move this 1 place, 2 places to the left, 1, 2, and we end up with 9.87. Okay? If you wanted to work it out, you could. You could turn these back into whole numbers. And so 2.1 times 10, right, gets you 21 if we think about it this way. 4.7 times 10 gets you 47. So that would give you 987, but then you'd have to divide by 10 times 10 is 100. And when you do that, you're back to 9.87. Okay? So let's look at this one here. Here the 21's the same, but the 47 is moved, right? So let's put it back to make it look like this one. So to make that into a 47, we'd have to multiply by, this is tenths, we want to move it 1, 2, 3 to the right, which means we got to multiply it by 1,000 to make it look like 47. So then you get 21 times 47 like we had before, and that equals 987, but we don't want to keep it like that because we multiplied by 1,000, we will now divide by 1,000 to move the place value 1, 2, 3, 3 to the left, 1, 2, 3, and we end up with 0.987. Okay, so we're just playing with the place value by multiplying by tens, hundreds, and thousands. Okay, same thing here. This one's already been moved 1, 2, 3 to the left, right? This has been moved 1 to the left. So in total, we've moved 3 place values here and 1 there. So in terms of zeros, we're talking about 1, 2, 3, 4. We've moved 10,000 places. So if I have a total of 4 place value moves, and I look at my number, which is 987, and I move it 4 places to the left, I would go 1, 2, 3, 4, and I have to have a 0 to hold that space there. And I put 0.0987 as a solution. Okay, so knowing this allows us to work in different methods, different strategies. I began with some dividing by 10 and then dividing by 100. I did some multiplying by 10 or multiply 1,000, and then I put it back by then dividing by the same number that I multiplied by. So you could do it without doing any math at all, just recognizing the place value moves and doing that to your solution, or you could do some math as well. Both ways work just fine. Let's look at activity number 3. Activity 3 is an optional one, so you may have done this in class, you may not have. Okay, and it says, let's use area diagrams to reason about multiplication. In the diagram, the side length of each square is 0.1 units. We see 0.1, 0.1, 0.1, 0.1, that's the length. Explain why the area of each square is not 0.1 square units. And why is it not that? Okay, so let's think about when could it be that. You see, if I had a square that was 1 by 1, we would say the area is 1 square unit because 1 times 1 is 1. That's okay, right? So normally you're thinking, well, that works there, right? So that would be a 1 by 1, no big deal. In this case here, 0.1 times 0.1 is not equal to simply 0.1, and that's what they want you to see. You see, 0.1 is the same as writing down 1/10. And so when you think about what I'm multiplying here, I'm not multiplying 1 times 1, I'm multiplying 1/10 times 1/10. And when you do that, yeah, on the top you still have a 1. 1 times 1 is 1. What happens to the denominator? We have 10 times 10, which is 100th, which means that this square has an area of 0.01. Okay? 0.01. How can you use the area of each square to find the area of the rectangle? Well, if I know that each square has an area of 0.01, and there are a total of 1, 2, 3, 4, 5, 6, 7, 8, I can multiply that by 8 to find the total area. 8 times 1 is 8, 8 times 0 is 0. I can see that I have 1, 2 behind the decimal, so I'm going to keep that, 1, 2 behind the decimal, and I have a total area of 0.08. Which makes sense because if I was to add this up, I'd have 0.1, right? If I did repeated addition, which is what multiplication is, I'd end up with a whole lot of 0.1s. Need more, 1, 2, 3, 4, 5, 6, 7, 8. You end up with 0.08. It makes more sense to do multiplication instead of repeated addition like that. All right? So explain how the diagram shows that 0.4 times 0.2 equals 0.08 is true. Well, what we see here is that if I think about 0.4, 0.4 times 0.2. Let's think about the one we did a minute ago. If I wanted to move this decimal over to make it a whole number, if I multiplied that by 10, I'd have 4. If I multiplied this by 10, I would have 2. And 4 times 2 is indeed 8, but now because I multiplied by 10 times 10, which is 100, I need to then divide by 100, so that's 8 over 100, which is 0.08. So we can see that if we change our decimal numbers into whole numbers and then put it back, we would end up with 0.08. So that's how that's going to work out the right way. Okay. Number 2 says, label the squares of the side lengths so the area of this rectangle represents 40 times 20. Okay, so if I want this to be a 40 times 20, then my side lengths, I have to do 40 divided by 4, which means each one is equal to 10. And 20 divided by 2, so each one's equal to 10. And that's what that would look like. That's 40 in this way, 20 this way. Okay, we're all right with that, I hope? Now the area of each square is going to be the length times the height, or the length times width, 10 times 10, which is going to be equal to 100. So the area of one whole square is 100. Use the squares to help you find 40 times 20 and explain or show your reasoning. Well, if I know that 1 is equal to 100, and I have a total of 1, 2, 3, 4, 5, 6, 7, 8, then I know that 100 times 8 is going to be 800. And that's going to be the same as 40 times 20, a length times a width, is also equal to 800. And you could try that out if you wanted to. You could test it to double check. 0 times 0 is 0. 0 times 4 is 4. Oops, sorry, 4. And then we move a space there. And we have 2 times 0 is 0. 2 times 4 is 8. And we have, oops, what did I do there? A little crazy. 0, 4. Oh, I know what I did. I wasn't thinking. Sorry. I should edit that out later, but I'll leave it because mistakes are just fine. 0 times 0 is 0. 0 times 4 is still 0. My pencil did the right thing, but my brain said no. Then we have a 0 there. 2 times 0 is 0. And then 2 times 4 is 8. So you end up with 800. And that makes a little bit more sense than my last one. In part 3, it says label the squares with their side lengths so the area of this rectangle represents 0.04 times 0.02. Okay, so we want this to be 0.04 across here and 0.02 across there. And again, they're squares. So to have 0.02, I end up with a side length of 0.01, because 1 plus 1 is 2, and a length across here also 0.01, 0.01, 0.01, 0.01. All right. Now, using the diagram there, we could figure out what the area is going to be. Now, the area here is 0.01 times 0.01 for 1 square, right? And 0.01 times 0.01 is going to be equal to 0.001. Now again, to find out what that area is going to be, I could use that number and multiply it by 8, because there are 8 squares, and we end up with 0.008. Right? That works just fine. I could also do 0.04 times 0.02 and come up with the same solution there as well. All right? I think we're right there. Oops, 0.008. What did I do wrong here? Back it up. 0.01, 0.01. We have 1, 0, 0, 0. Oh, we got to put 4 decimals. I'm so sorry. 4 behind the decimal. 1, 2, 1, 2. Wasn't counting right there. Sorry about that. Working too much. So you end up at 0.008 is what our area is going to be there to figure that out. And again, you could add that up. This one here should also be 0.008. I'm so sorry. I should just redo this whole section, but I don't have time. So I'll leave it like that and make some corrections for you. All right, so that's the idea. My better numbers are here. Sorry, I had to fix that one, fix that one, fix that one. Boy, a lot of fixes there. So hopefully you get the idea there. You can multiply and get them figured out yourself. Let's take a look at a summary real quick for this lesson. All right, just kind of what we've talked about here. We talked about how we can look at 0.04 and 0.07 and then multiply them by powers of 10 in order to turn them into whole numbers, which is just fine. And then we can do simple multiplication, but then because we multiply that, we have to then do the reverse, which is divide by that same thing in order to put it back into decimal form. We can also write decimals as fractions and just do long multiplication problems with fraction numbers and end up at the same place. And so either way, you end up with the same solution, just 2 different ways of doing that. And then we can also use an area model just to kind of visually show how that works out and how we end up with the same solution there, which we did in our practice as well. Of course, my numbers are wrong, but you know, hey, we got them figured out at the end. Okay, all 3 calculations show you that you end up with the same solution, which is 0.0028, and you're good to go. Okay, we're going to pause there and let you start your homework. We'll come back together and check it together in just a minute. Okay, here we are on Math 6, Unit 5, Lesson 6, doing the homework for methods of multiplying decimals. And again, for some of these today, I'm going to show you one way of doing them, but there are multiple ways of solving these problems. So if you do it a different way, that's okay. Again, always just be ready to show your reasoning to your teacher when they ask you for that, okay? So find each product and show your reasoning. So this first one, maybe perhaps on the first one, we have 1.2 times 0.11. And maybe we decided let's get rid of those decimals by, first of all, multiplying this by 10. That becomes 12. And this one I move the decimal 2 to the right, so I'm going to multiply by 100 to come up with 11. So 12 times 11 is actually equal to 132. Now, those are the whole numbers. I am working with decimals though. So now to put this in the right decimal form, I need to divide by whatever this is. 10 times 100 is 1,000, so that's 1,000, like so, which can be written as 132 over 1,000, or as a decimal, if I want to write it as I do 132 thousandths. I think about the places. I have tenths, hundreds, thousands. I want that number to end up in the last spot there, so I put my decimal here, and I end up right there, 0.0132. So that's one way you could solve letter A. For letter B, we could do something similar, right? I could do 0.34, and I can multiply that by 100, so I end up with 34, and that's all multiplied by 0.02. I'll multiply that by 100, so I have 2, Okay, and 34 times 2 is 68. So what's kind of nice is I know what 34 by 2 is. That's not too bad. It's pretty much mental math, right? That's okay. So now I do 68 and I divide by the combination of this. 100 times 100 is 1, 2, 3, 4 zeros, 10,000, right? So that's the same as 68 over 10,000. So I think of place value, where am I going to put the 68 at? Okay, I have my ones place, my decimal, my tenths, hundredths, thousandths, and 10,000ths. So I want to make sure the 68 ends up in the 10,000ths place. So I put an 8 there, a 6 there, and I backfill those zeros so it looks like that, and we have 0.0068. For letter C, this one is in the thousands place, so it's 1, 2, 3. So I multiply this by 1,000, so I end up with 120 times 2, and that's going to equal 240. And I divide that by the same 1,000, and that's going to be equal to, and this is 240 thousandths. So again, think about ones, tenths, hundredths, thousandths. I want this to be at the 240. The 40 is at the thousandths place, so I have 0.240. Sorry that's so small right there for C, but I ran out of space, but that's the way that works. Okay, number 2. You can use a rectangle to represent 0.3 times 0.5. So this is 0.3 times 0.5, which makes this 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, 0.1, like so. So what must the side length of each square represent for the rectangle to correctly represent that? Well, 0.1, like we did, because when you add those up, 0.1 plus that is equal to 0.3. So the area of one square is 0.1 times 0.1. And I can write 0.1, that's fine. Or another way of thinking about it, it's 1/10 times 1/10, which equals 1/100th. So 0.01 is the area of one square. So now when I look at these squares, I have a total of 15 of these. Okay, so how would I show the reasoning there? Well, that's going to be the same as thinking a couple ways. I could do 0.01 times 15 because there are 15 squares. I could look at this and multiply this by 10 to have 3 times 10, which becomes 5. And 3 times 5 is 15. And now I divide it by 10 times 10 is 100, divided by 100. So I get 15 over 100, or 15 hundredths, like this, right? And again, hundredths is here because why? Ones, tenths, hundredths, 15 hundredths, right, like that. So this also equals that, and this equals that. A couple ways of going about it, and you're good. Number 3. 1 gallon of gasoline in Buffalo, New York costs $2.29. In Toronto, Canada, 1 liter of gasoline costs $1.91. There are 3.8 liters in 1 gallon. How much does 1 gallon of gas cost in Toronto? Okay, so in Toronto, you're going to buy 3.8 liters to make 1 gallon. Okay, because it's Toronto, I'm going to buy 3.8 liters. Now, 1 liter costs $1.91. Okay, so I need to take my 3.8 liters to make a gallon, right? This is my gallon, and multiply it by how much it costs for 1 liter. I'm going to buy 3.8 liters in order to have a gallon, and it's going to cost me 91 cents for each liter I buy. So I'm multiplying 3.8 times the 91 cents, and how you want to solve that, again, that's up to you. You could do it different ways. Okay, I could, like we've been practicing, I can multiply this by 10, so that I have 38 times, and multiply this to move to the right 2 places, times 100, so times 91, and 38 times 91 is 3,458, okay, and then to put it back in decimal form, what I could do is say this is 100 times 10, which is 1,000. If I divide this by 1,000, that means I'm moving the decimal how many places to the left? 1, 2, 3. So we write 3, 4, 5, 8, and move it 3 to the left. So we go 1, 2, 3. So we have $3.45.8. Again, it says to round to the nearest cent, so I'm going to round up a little bit there. And we would say that really we're at $3.46. I'm going to round up 58 to 60. All right, so there's that one. If the cost is the cost of gas greater in Buffalo or in Toronto? So Buffalo, it costs me $2.29 for a gallon, and in Toronto, it costs $3.46 a gallon. So we would say that Toronto costs more. So Toronto is the more expensive place to buy gasoline. So buy your gas in Buffalo and then head on across the border to Canada and visit your friends. All right, number 4, calculate each sum or difference. Oh, here we go. 10.3 plus 3.7. So we can stack this one vertically like so. 7 plus 3 is 10. 1 plus 0 plus 3 is 4. Keep my decimal. And 1 plus nothing is 1. So we have 14. 20.99 minus 4.97. 9 minus 7 is 2. 9 minus 9 is 0. Keep my decimal point. And 20 minus 4 is 16. 15.99 plus 23.51. 9 plus 1 is 10. 9 plus 1 is 10 plus 5 more is 15. Keep my decimal point. 5 plus 3 plus 1 is 9. And 1 plus 2 is 3. And then finally, 1.893 minus 0.353. 3 minus 3 is 0, 9 minus 5 is 4, 8 minus 3 is 5, keep my decimal point, and 1 minus 0 is 1. So 1.540 for that one right there. All right, let's turn the page and look at number 5. Number 5 says, find the value of 49/50 divided by 7/6. Use any method that you like. Okay, well, my method is look at the teacher's book and write down the answer. Nope, that's not what I'm going to do. So let's do 49 divided by 50, and we're going to multiply by the reciprocal. Okay, so we're going to multiply this by 6/7. And I like this method for this one because I noticed that 7 and 49 have a common factor, right? 7 goes into here 7 times, so that's nice to reduce that there. This one here, I recognize that they're both whole numbers, or sorry, even numbers, so I can divide them by 2. This is 25, and that becomes 3. And I don't see anything else I can divide by or reduce by, so I'm going to leave it like that. 7 times 3 is 21, and 25 times 1 is 25. And we can leave it just like that. Number 6. 6 is a great problem in that it's a funny little shape, and I want you to find the area of the shaded region. And there's a couple ways of going about this. Okay, you could try to slice this up and figure out what each of these pieces are going to be, right? You could slice it like so, right there, like that. That could work. When you slice this one up here, this one's a little different to slice up. Maybe I slice it across like this a little bit. You know, I could probably do something like that, and then find the 3 pieces. That could work out okay, right? This would be 350 times 10, which is 350. This looks like a 10 times whatever that length's going to be, which is 60, the whole thing. So that's going to be 600. And here, this length's different, right? I know that this is 15 to go from here to here. That's 15. And then I have this part, which I don't include this 15 there in the 60, so it's whatever's left, which is going to be a total of, right, if I have 60 minus 15, then I'm sitting at 45. I've already used 15 of them, so this is going to be 30. So then I have a 30 and 15, which is 45, times 10, which is 450, and I got to add those up to have 350, 600, and 450. And when I add them up there, I end up with 1,400. That works there as well. Another strategy you could use is you could figure out, well, let's find out the area of the cutoff parts and subtract them, okay? This is a 10 by 10 area here, so this is going to be equal to 100. 15 by 10 is 150, and 15 by 10 over here is also 150. So those squares have a total of 150, 150, 100, which is a total of 400. The whole square, or the whole shape itself, is 60 times 30, and 60 times 30 is equal to 1800. So if I subtract off those three corners, I'm left with 1400. Those answers are the same, they both work. So there's two different ways of approaching it. I could slice this up and then find the areas of the little pieces, or I could do the whole thing and subtract the corners. Either one works, just make sure you explain your answer there. Okay. Number 7. Priya finds 1.05 times 2.8 by calculating 105 times 28, then moving the decimal point 3 places to the left. So 3 places to the left is 1, 2, 3, is like by going to the left is going to be dividing by 1,000. If I want to go to the left, right? So 1, 2, 3. Does that make sense? Well, let's see. To go from 1.05 to 105, that's multiplying by 100, because 100 moves it 2 to the right to get 105. To go from 2.8 to 28, I'm multiplying by 10. Oh, I don't know, I have 2 x's there. That gets you 28. So that's how you end up with 105 times 28. That's okay there. Now let's see. This is a combined of multiplying by 100 times 10 is multiplying by 1,000. So in order to put it back, we would then divide by 1,000, which is 2, 3 to the left. And we're good there. That's okay. So we would agree, we'd say, yes, that's great. Great job. Works out just fine. Okay. And use Prior's method to calculate 1.05 times 2. Use the fact that okay, so great. So knowing this, we're going to do our number 2940. Move to the left 3 places. 1, 2, 3. We have 2.940. Works out well. Now use that to multiply to do this one. Okay. Well, here we have 15 and 24. Okay. Now 15 times 24 is equal to 360. Okay. Now, to make this work, we see that we're moving 1, 2, 3, 4. Okay, 4, which is times 1, 2, 3, 4, 10,000. This is moving 1, 2, 3 to the right, times 1, 2, 3 to the right. When I combine those together, that's going to be 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So that's 10 million. That's a crazy number. So I'm going to have to divide by 10 million in order to figure out what that 360 is going to be. So here's how this works. We take our 360 and we go by how many zeros? 1, 2, 3, 4, 5, 6, 7. And we'll go 7 to the left. 1, 2, 3, 4, 5, 6, 7. Put our decimal point. Now let's fill in those spaces. So 0, 0, 0, and 0. And that becomes our answer. Alright, so does that work out? It works out just fine. Okay, that's it for today. Have a great day, and we'll see you next time.